We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh?
When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 118 of the Space Rocket History Podcast. And now, Apollo, Lunar Module Design, Part 2. Last week we began our study of lunar module design. We covered external design, the cockpit, the seats, and windows. Before we continue, I want to make sure everyone understands the complexity of the task and how much was still unknown. These are the words of Michael Collins, who would become the command module pilot for Apollo 11. Quote, in 1964, in Houston, a lot of answers had still to be provided before any rational person could assess the chances of success. Eminent scientists like Tommy Gold of Cornell fretted over a possible dust layer on the surface of the moon, whose thickness might just exceed the height of the lunar module. Others postulated a chance of static electricity on the limb, which would cause whatever dust was there to become attracted and adhere to the ladder, obscuring the astronauts' view out the windows. Lunar soil was thought by some to contain pure metallic elements, which, when introduced on dirty boots into the pure oxygen in the limb cabin, would spontaneously burst into flame. Meteorites were known to exist in space, and with no atmosphere to protect it, the moon would clearly be an inviting target for them. End quote. In addition, there were concerns with micrometeoroids and solar flares, just like we covered for the command module. I want to begin today's episode with the lunar module's hatches. The lander originally had two docking hatches, one at the top center of the cabin and another in the forward position or nose of the vehicle, with a tunnel in each location to permit astronauts to crawl from one pressurized vehicle to another. And at this time, even extravehicular transfer between craft still remained as an emergency backup method. But the plan was, after injection into a translunar trajectory, meaning a course toward the moon, the command module pilot would turn his ship around, fly up to and dock with the lander's upper hatch, and then back the two vehicles away from the spent S-4B third stage. This top-to-top docking arrangement aligned the thrust vector of the service module propulsion engine with the centers of gravity of the two spacecraft, thus avoiding adverse torques or tendencies to tumble during firings for mid-course corrections and injection into lunar orbit. This is the same hatch the crew would enter the lunar module. Originally, when the lander returned from the moon, the front hatch would be used for docking and crew transfer, because there were no windows in the top of the lander. Thus, the lunar pilot would be flying blind if he docked using the upper hatch. One of Grumman's human factor experts later said, in an apt analogy, "It would be nice to see the garage when you drive into it." By spring 1964, NASA and Grumman engineers were thinking of deleting the front docking procedure and adding a small window above the lunar module commander's head. This overhead window might add 7 kilograms of weight and some extra thermal burden, but cabin redesign would be minimal. The added weight would be offset by eliminating the front tunnel and the extra structural strength needed to withstand impact loads in 2 areas. And eliminating forward docking had another advantage. The hatches could now be designed for a single purpose: access to the command module through the upper hatch and access to the lunar surface through the forward hatch, which certainly simplified the design of the forward hatch. So, NASA directed Grumman to remove the forward docking interface, but to leave the hatch for the astronauts to use as a door while on the moon. Once the location of the hatches was settled, getting the astronauts out and onto the lunar surface had to be investigated. Remember, the astronauts were in the ascent stage, or second stage, of the LEM. Now at this point it got a little strange. While using a cable contraption called a Peter Pan rig to simulate the moon's gravity, Grumman technicians tried to figure out how the crews could lower themselves to the lunar surface and to climb back into the spacecraft. First, they tried a block and tackle arrangement and a simple knotted rope. Yes, I said a knotted rope. When astronaut Ed White, among others, scrambled around a mock-up of the lander using a block and tackle arrangement and a single knotted rope, he found that both were impractical. So, in mid-1964, a porch or ledge was installed outside the hatch, and a ladder and handrail was installed on the forward landing gear leg. Here's a clip on the ladder decision from aerospace historian Josh Stoff.
In the early concepts for a lunar lander, there's no ladder on the front leg. Because why do they need a ladder? There's only 1/6 gravity on the moon. What if we just give them a rope that they hang from the hatch down to the lunar surface? They climb down a rope, they climb back up it, we save weight. Grumman builds a full-scale wooden mock-up. Astronauts try climbing down the rope. Nobody can get back up the rope. So they had to add a ladder down the front leg.
Then there was another discovery. While testing on the mock-up, the astronauts discovered that they had trouble squeezing through the round hatch in their pressurized suits and wearing the bulky backpacks. Therefore, the forward hatch was squared off to permit easy passage. All these design features, although unusual, appeared to be compatible with the lunar environment. At least the engineers did not entertain any special worries. But the landing gear was different. The design of the legs and foot pads depended on assumptions about the nature and characteristics of the lunar surface. In absence of any firm knowledge and with scientific authorities differing radically in their theories, how should one design legs to support a craft landing on the moon? Here's a clip on the landing gear from the father of the LEM, Thomas Kelly.
The design of the landing gear is an interesting story in itself. Now, this was influenced by a couple of factors. It was influenced by the theories as to what the lunar surface might consist of. They varied all the way from a very light, powdery dust into which the whole LEM might sink. That was one extreme. The other extreme was that it was going to be ice, very slippery, very hard in some areas.
Now here's a word from Joe Gavin, director of the Lunar Module Program at Grumman.
You must remember how many things we didn't know at the very beginning. This expert was telling us that there are 10 meters of impalpable dust on the surface of the moon. And we worried tremendously about tipping over. In fact, we made, I think, something like 400 different computer runs because we didn't understand what the dynamics of the landing would really be.
Grumman had first considered 5 legs for the limb, but during 1963 decided on 4. The change was dictated by the weight versus strength trade-off that had produced the cruciform descent stage with its 4 obvious attachment points. The revised landing gear pattern also greatly simplified the structural mounting of the vehicle within the adapter. 4 legs set on the orthogonal axes of the lander, forward, aft, left, and right, mated ideally with the pattern of 4 reaction control quads, meaning the basic 4-engine package. The engine package was rotated 45 degrees so the downward thrust attitude control engine fired between the 2 nearest gear legs, overcoming a severe thermal problem of the 5-leg arrangement. While Bethpage was wrestling with the legs, Houston decided it had been too optimistic about the load-bearing strength of the lunar surface in the request for proposals. The resulting revision placed heavier demands on the landing gear, and Grumman had to enlarge the foot pads from 22 to 91 centimeters in diameter. The bigger feet made the gear too large to fit in the lunar module adapter on the Apollo stack. A retractable gear therefore replaced the simpler fixed leg gear. Retractability also figured in the shift from 5 to 4 legs. The fewer to fold, the better. Lunar landing leg experts at Grumman had to change the geometry of the undercarriage, devise the best structure for impact absorption and stability upon landing, and choose the most suitable folding linkages. Grumman had 3 design choices for the folding legs. First, landing gear that tucked sideways or laterally folding. Second, a tripod arrangement that was radial with 3 struts meeting at the base just above the footpad. And third, a cantilevered device with secondary struts for extra strength that folded inward against the vehicle for storage and braced the leg when deployed for landing. Houston and Bethpage selected the cantilevered version. Somewhat narrower than the radial one, it was in many ways more stable. It had other advantages, such as less weight, shorter length for easier stowage, and a simpler and therefore more reliable folding mechanism. While this was going on, there was a broad program of computer-assisted analysis at Houston and Bethpage used to determine the worst conditions for impact. The studies were reinforced by drop tests of lander models at Houston, Bethpage, and Langley. There were also plans to drop test full-size test articles to check out the new designs. During 1963, Grumman engineers continued to worry about the nature of the lunar surface and to carry on theoretical and simulation studies of lunar geology and soil mechanics. With the support of such consulting firms as the Stevens Institute of Technology in New York and the Arthur D. Little Company in Massachusetts. Much of this work covered the interaction between vehicle and surface at the moment of landing. What would happen to the landing gear at touchdown? Would the lunar dust that might be kicked up by the descent engine exhaust obscure the landing site? Would soil erosion affect the stability of the lander? Washington assisted in this research. In mid-1963, Belcom surveyed all that was being done inside and outside NASA and suggested that a backup gear be developed in case the surface should be more inhospitable than it appeared. Lastly, a landing gear for the lunar surface had to be designed for varying landing conditions such as protuberances, depressions, small craters, slopes, and soil-bearing strength. To achieve the necessary stability, the landing gear had to be able to absorb a diversity of impact loads. Houston and Bethpage met this challenge by using crushable honeycomb materials in the struts, so the gears would compress on impact. A principal advantage of honeycomb shock absorbers was their simplicity, since they had to work only once. The more common hydraulic shock absorbers and their complexities could be avoided. Subsequently, crushable honeycomb was also applied to the large saucer-like foot pads to improve stability further for landing. Now let's turn our thoughts to the engines required for the lunar module. When Grumman began designing the lunar module in January of 1963, its major subcontractors began work on the vehicle's integral subsystems. Bell Aerospace worked on the Ascent engine, Rocketdyne Division of North American worked on the Descent engine, the Marquardt Corporation worked on the reaction control system, and Hamilton Standard, a division of United Aircraft Corporation, worked on the environmental control. Grumman believed the rocket engines were the most critical subsystems, so they started their development first. The lander had 18 engines, 2 large rockets, one for descent to the moon and another for return to lunar orbit, and 16 small attitude control engines clustered in quads and pointing up, down, left, and right around the ascent stage. Bell Aerosystems was hired during the spring of 1963 to develop the Ascent engine because of their experience in Air Force Agena development and hoping that the technology from that program might be applicable to the lunar module. Grumman placed heavy emphasis upon high reliability through simplicity of design, and in fact, the Ascent engine did emerge as the least complicated of the 3 main engines in the Apollo space vehicle. The descent and service modules were the other 2. The engine of the Ascent stage was designed to develop 3,500 pounds of thrust, which produced a velocity of 2,000 meters per second from lunar launch to docking. The Ascent engine employed a pressure-fed fuel system using hypergolic, meaning self-igniting, propellants. The Ascent engine was fixed thrust and non-gimbaled. It was capable of lifting the ascent stage off the moon or aborting a mission should a landing not be feasible. One of the concerns about the Ascent engine was that the ablation material might burn off too fast and cause damage to the thrust chamber. Some ablative material eroded during firing tests at Bell's plant near Niagara Falls and at the Arnold Engineering Development Center in Tennessee, but this erosion was not severe enough to warrant changes in the combustion chambers. Not everything went well with the Ascent engine development. About a year after the program began, the subsystem manager in Houston discovered that Grumman and Bell were using testing criteria left over from the Air Force Agena program. Since the Agena was unmanned, these tests were less stringent than NASA demanded for manned spacecraft. More rigorous standards were belatedly imposed by Houston, and a problem was revealed. In bomb stability tests, where the engine had to recover from combustion instability caused by an explosive charge within the combustion chamber, the ascent engine went unstable, and structural damage followed. This problem would have to be resolved before the engine could be trusted to bring a crew back from the lunar surface. Now here's a clip from Thomas Kelly describing some other concerns about the ascent engine.
You're totally dependent on the ascent engine to work to put you back in orbit. If for any reason the ascent engine failed to work, the astronauts are doomed.
To keep it simple, it used so-called hypergolic propellants, a rocket fuel and an oxidizer that explode on contact. There were no pumps and no igniter. But the simplicity came at a price. The fuels were extremely toxic.
We got so familiar with what oxidizer looks like when it leaks. You have this big red cloud. You couldn't absorb more than 5 parts per million on a continuing basis. It would start to eat your lungs away. So if we had a spill, and if the wind was just right, we had to get the police out and get people to evacuate.
But what really worried them was that the fuel was so corrosive that at the end of a test, each engine had to be rebuilt. It meant the final assembly of an engine could never be tested.
Unbelievably, the first time these engines would ever have been fired, ever. No checkout at the factory. The first time would be when they were fired in their mission. Imperfection was not an option. They had to be perfect.
It was a situation nobody at Grumman would ever feel comfortable with.
Now we'll move on to the descent engine. The descent engine was designed to reach a maximum of 9,870 pounds of thrust. Some have called this descent engine the biggest challenge and the most outstanding technical development of the Apollo program. This is because the descent engine was required to throttle, which was new to manned spacecraft. Very little advanced research had been done in variable thrust rocket engines. NASA's principal effort in this field was the hydrogen-fueled RL-10, which was used in the S4 stage of the Saturn. This only predated work on the lunar module engine by a few months. Rocketdyne proposed a method known as helium injection, introducing inert gas into the flow of propellants to decrease thrust while maintaining the same flow rate. Although Bethpage and Houston agreed that this seemed a plausible approach to throttle ability, it would be a major advance in the state of the art, and the MSC Apollo office directed Grumman to carry out a parallel development program and select the better design. On March 14, 1963, Grumman held a bidders conference attended by representatives from Aerojet General, Reaction Motors Division of Thiokol, United Technology Center Division of United Aircraft, and Space Technology Laboratories. In May, Space Technology Labs was selected to develop the competitive motor. They proposed a pressure-fed hypergolic system that was gimbaled as well as throttleable. The engine's mechanical throttling system used flow control valves and a variable area injector in much the same manner as a shower head does, to regulate pressure, rate of propellant flow, and pattern of fuel mixture in the combustion chamber. With two subsystem contractors working on such radically different throttling techniques, NASA planners believed one of the methods would prove unworkable soon, so it would quickly allow them to concentrate on the other method. But that didn't happen. Both methods seemed acceptable. Space Technologies Lab and Rocketdyne continued this head-to-head competition for the final and lucrative engine development and qualification contract through the end of 1964. In November of 1964, Joseph Shea, Apollo spacecraft manager in Houston, told NASA Apollo program director Samuel Phillips in Washington that he had established a committee of propulsion experts from Grumman, the Marshall and Lewis Centers, NASA headquarters, and the Air Force to review the contractor's efforts and recommend a choice. Selection of one firm over the other rested with Grumman and MSC. Panel members visited both companies the week of December 7, 1964, but their findings were largely inconclusive. The progress of each firm was nearly identical. Both contractors, although experiencing minor troubles with injector designs, demonstrated satisfactorily structural compatibility between injector and thrust chamber. After a year and a half, neither helium injection nor mechanical throttling had proved superior to the other. But on January 5, 1965, Grumman decided to stick with Rocketdyne. Manned Spacecraft Center Director Gilruth appointed a 5-member board to weigh Grumman's recommendations. On January 18th, this review board, in a surprising move, reversed Grumman's recommendation and named Space Technologies Lab instead of Rocketdyne. The board said that the recommendation was based upon the assessment that Space Technologies Lab was in a more favorable position and was capable of supplying more management and superior resources to the program without interference of other similar programs. Additionally, there were potential benefits to be gained for the Gemini and Apollo Attitude engines programmed at North American Aviation by the cancellation of the Rocketdyne descent engine development. In other words, Rocketdyne was too busy with important NASA projects and Space Technology Labs was not. This decision was unusual because Houston rarely vetoed a recommendation for a subcontractor made by a prime contractor. Shea and contracting officer James L. Neal then directed Grumman to proceed with Space Technologies Laboratory. Now moving on to the third engine system. Grumman chose Marquardt to build the lunar module's small 100-pound thrust attitude control thrusters. In 1960, Warren P. Boardman and Maurice Schleck of Marquardt had visited Robert Pylon and Caldwell Johnson at Langley to discuss their firm's propulsion work. Pylon and Johnson were intrigued with the idea for a bipropellant thruster that promised to be far superior to the monopropellant engine then used in Mercury. Testing of Marquardt's product, a dual-valve pulse-modulated engine with a radiation-cooled combustion chamber at the Lewis Research Center, paved the way for its incorporation into Apollo. Marquardt at first supplied engines for both the command and service modules. In mid-1962, NASA decided to use the Marquardt engine for the service module only because the command module thrusters would be buried within the heat shield, making radiant cooling impossible. Rocketdyne would supply the command module thrusters, which were similar to those it was already developing for Gemini. Marquardt would furnish attitude control engines and mounting structures and perform some tests of the propellant system. Grumman would provide tanks purchased from Bell, propellant lines, and the pressurization system. Apollo officials had expected that the service module thrusters, with only slight modifications, could also be used in the lander, but common use proved difficult. The end results, though beneficial, fell far short of Houston's anticipations. Differing functional requirements as well as unique environmental and design constraints precluded direct incorporation of the service module thruster. Houston, however, complained that Grumman failed to take advantage of all the common use technology available and attributed delays in procurement of many thruster components to this failure. After thruster tests at Bethpage and at Marquardt's Magic Mountain facility in California during the first half of 1964, a technical problem emerged. The engine spiked or backfired at ignition, and a rapid rise in temperature and pressure caused the engine to explode. The spiking appeared so significant that Grumman wanted to develop a backup engine through another source, but Houston refused permission. Marquardt eliminated spiking by installing a small tubular pre-combustion chamber inside the engine. Now let's change the topic to the environmental system. Grumman selected Hamilton Standard to supply the environmental control system for the lunar module. Like AI Research's unit in the command module, it was a closed-loop atmospheric circulation system using supercritical oxygen and non-regenerative removal of carbon dioxide to provide a pure oxygen atmosphere. The system also had a liquid circulating network and heat absorbent panels to maintain a comfortable temperature inside the cabin. By mid-1964, Hamilton Standard had finished the design phase and begun fabrication and testing. Occasional problems arose during development, but none that threatened the manufacture of a successful subsystem. Now the final topic I want to cover is the LIMS electrical system. United Aircraft Corporation's Pratt & Whitney Aircraft Division was a pioneer in research on fuel cells using hydrogen and oxygen as reactants to generate electricity. Grumman picked this firm in July 1963 to develop the power system for the lander. The fuel cell program was laden with technical and managerial problems. Many of the lander's components operated with considerable independence, but the electrical system had a complex interrelation with virtually every subsystem in the vehicle. The question of how many fuel cell stacks and how many tanks of reactant were needed to meet electrical requirements was therefore difficult to answer. In March of 1964, Houston approved a 3-cell, 5-tank arrangement, but by summer, the fuel cell was in deep technical trouble. NASA and Grumman engineers concluded that it might take more than a year to get the cells working with the other system properly. The lunar module, which had begun development a year late, did not have time to spare. Houston told Grumman in late 1964 to consider substituting batteries for fuel cells, and on February 26, 1965, Bethpage was ordered to make the change. Although the switch was not entirely welcome to the lunar module design team, it caused no appreciable delay, and to some it came as a distinct relief. The beauty of batteries lay in their simplicity, hence their reliability, in contrast to the fuel cells. Some of the battery development costs could be offset by the cancellation of the Pratt & Whitney contract. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.